Ampere's law. The figure shows three wires, each at a particular point in a Cartesian plane, carrying current out of the page. So you can see here we have the origin, and then we have a 2 amp current coming through this wire towards us out of the page, and that wire is at a location 4,0 meters. Then we have another wire here. This is 4 amps of current, and then we have one more here, 9 amps of current at -4 meters, 1 meter. Here we have a distance of 5 meters from the origin. We've shown that with dashed lines. State why we cannot use Ampere's law to determine the magnetic field magnitude at the dotted location shown where R is 5 meters from the origin. Ampere's law is mu naught times the I enclosed, and that equals that dot product right there. You might think, well, inside this radius, we have a certain amount of current that's inside there, so we should be able to use Ampere's law. However, remember the deal with Ampere's law is that to use it effectively, the magnetic field has to have the same magnitude at each point around your Amperian loop. And that is definitely not going to be the case for this scenario. You can see a point right here where my marker is. That would have a very strong magnetic field because it's really close to that 9 amp current. Whereas a point over here, well, it's relatively further away from everything. So most likely the magnetic field right there is going to have a different magnitude. And so you can't use Ampere's law for R equals 5. But what about this? State why we can use Ampere's law to get an extremely good estimate of the magnetic field magnitude at a distance of R equals 100 meters from the origin. And then let's calculate that numerical estimate. Why is it okay for R is 100, but not R equals 5? When R equals 100, let's draw a little Amperian loop. And let's say that it has a radius of 100 meters. You see, when the radius is really big like that, these wires, they're less than 5 meters away from the origin. So it's almost as if all of those wires, and we have 9 amps out of the page, 4 amps out of the page, 2 amps out of the page, that's a total of 15. It's almost as if all 15 amps are coming out right at the origin. Now, it's not exact, but the further away we get, it looks like there's just 15 amps coming out. When R is very large, the situation is roughly equivalent to having simply a 15 amp current at the origin. So let's use Ampere's law. Mu naught I enclosed equal to that integral right there. And we said that when we're 100 meters away, the magnitude of the magnetic field for each point around the loop is pretty much the same, which means B can be considered a constant, which means I can move that integral sign over there. And we said when you integrate around a circular Amperian loop, it's just 2 pi r. So what's the magnitude of the field? It's going to be mu naught times the I that's enclosed divided by 2 pi r. We've seen this equation a whole bunch of times, but we haven't often used numerical values in it. Mu naught is a constant, 4 pi times 10 to the -7th with the proper units. The I enclosed is 15 amps. And then down here, we're going to divide by 2 pi. You can see that the pi cancels out, and the distance away is 100. You crunch that out to one significant figure, you get about 3 times 10 to the -8 Teslas.